So, in the last video we have derived orthogonal property. We are giving some properties of Legendre polynomials. First property is the orthogonal property, was the most important property, and in that we have seen that any two different orthogonal two polynomials, Legendre polynomials will be orthogonal, and we have seen that if you take the same polynomial when you integrate, so you will have some value. So, while doing that, so in this video, so we will derive another expression directly from the recurrence relation of the Legendre equation, from which you can directly derive this formula for the Legendre polynomial p n x. Okay. So, before I do that, so in the last class, last video we have done this integral value. So, we have seen this integral value as this. Okay. So, you can see that so 2 times, and you do that dt by, so the 2 actually cancels. Okay. And you are doing it, so x square, so x 2x dx equal to dt. So, when you are replacing with dx, which is dt by 2x, so the 2 cancels, 1 by x is actually t power minus half. So, you do not have this 2. Okay. So, this value you will see that is actually this one. So, 2 times, finally you see that this is what you will get. Okay. So, we will see that how it is done today. So, what you need is this beta function at half n plus 1, which is gamma half into gamma n plus 1. So, n is a natural number. So, you can find this n plus 1 plus half. Okay. So, this is equal to, so gamma half is root pi, and this is n factorial divided by this. You can write using this formula as n plus half into gamma n plus, so gamma n plus half. Okay. So, again, so you can rewrite like n plus half. So, it is actually n plus half. N plus half I write like n minus 1 plus 1 plus half. So, it is again like right. Okay. So, half plus 1, rather n minus 1 plus half plus 1. So, this is actually this. Okay. And you actually see n plus half plus 1 is n plus half into gamma n plus half, 1 goes. I just added and subtracted 1. So, again you can rewrite gamma root pi into n factorial divided by n plus half times again n minus 1 plus half, that is n minus half. So, it is going to be n minus half into gamma n minus 2 plus half plus 1. So, that is what you will see. What is this actually? N minus 1 plus half, n minus half. So, n minus half into gamma n minus half. Okay. So, like that you go on every time you do this. This is actually n minus half. N minus half, I am rewriting n minus 2 plus half plus 1. Okay. So, next time when you write n minus 3 plus half plus 1 will be, this is actually this is this into gamma of this into n minus whatever is here. So, this is going to be n minus 2 plus half, n minus 2 plus half is n minus 3 by 2. So, this into this is actually equal to this. So, you can replace like this, go on, you can go on like writing like this. What you see is you will end up n minus 3 by 2 and so on. Finally, you end up so you will end up just 5 by 2. So, if you keep on adding, so n is a fixed number, fixed natural number. So, you have 3 by 2. So, you see that 5 by 2, 3 by 2, and you finally get 1 by 2. So, when you get a 1 by 2, when you get 1 by 2, gamma will be n equal to 1 in this case, for example. Okay, n equal to 1, this is n half plus 1, that is half into gamma half. The gamma half is again root pi. So, this root pi goes. Okay. So, you can easily see that this is going to be n factorial divided by, if you write 2n plus 1 divided by 2, this is going to be 2n minus 1 divided by 2, this is going to be 2n minus 3 divided by 2, and so on, 5 by 2, 3 by 2 and 1 by 2. This is what you have. So, in between you add 2, 4, 6, okay, and so on. You have here 2n minus 2, you have 2n. So, what you added 1, 2, 4, actually 2, 4, 6, 8 up to 2n, that is actually 2 power n into n factorial. Okay. And you see this, how many are there? I have in the division 1, 2, 3, 4, 5 up to I have n plus 1 you have in between. Okay. These denominating these 2's in the denominator, how many are there? If n equal to 2, this is going to be 2 into 2 plus 1, 5 by 2, 5 by 2 up to here. So, if n equal to 2, I have 3 2's. If n equal to 3, 7, 7 by 2, that means I will have 4. So, if n equal to 3, I am getting 3. So, like that, if you have n, you will have n plus 1 2's. Okay. These you can take it up, bring it up. So, what you have is n plus 1 into 2 power n into n factorial divided by, now this is 1, 2, 3, 4, 5 up to 2n plus 1 factorial divided by 2 power n plus 1, that will go here. Okay. So, this is equal to n factorial square 2 power n factorial into, rather you write 2 power n factorial whole square into 2, 1 2 divided by 2n plus 1 factorial. This is exactly what you have here, this is what you get. Okay. So, let us see how we get a different formula for the Pn of x, a new formula. Okay. A new formula for Pn of x. So, this is also one kind of property. Okay. And so, we have seen the one property, that is the Pn's are orthogonal. Okay. So, Pn Pm actually satisfying orthogonal property. So, we have seen this orthogonal property, that is as a property 1, and you see that another second, if you want to write it as a property, second property is property 2, you can write Pn of x, n is from 0, 1, 2 onwards, or n belongs to z, in fact any z. Okay. Any integer n you have is a bounded solution, is a bounded solution for the Legendre equation. Legendre equation, what is that equation? Y double dash 1 minus x square minus 2x y dash plus n into n plus 1 y equal to 0. So, this is what you have. Okay. So, this is what, so you see that this x is between, so you have minus 1 and 1 are singular points, but this function is defined even at, because these are polynomials, you have a solutions which are as a functions, they are defined everywhere, but as a solutions they are actually valid between minus 1 to 1, even at those points minus 1, 1 they are actually bounded. So, its value is defined. Okay. So, that is the, so you see that this is a bounded solution. So, you have a bounded solutions for this equation. So, that is you can take it as property. We will give now a new formula for this. So, to give this, let us go back to the equation. So, what we have done when we started solving this equation, what we derived is, you put it as series solutions. When you put the series solution, you get a recurrence relation like this. When you equate this x power 0, n equal to 2, n equal to 3, okay, what you have is this, and now what you have is this one. So, this is, so where is the recurrence formula? You have a recurrence formula here. So, what you have is this is equal to 0, this formula is called recurrence relation. If this is equal to 0, you have a, when you substitute the power series solution into the equation which is equal to 0, all the powers of x power n coefficient should be 0. So, this is the recurrence relation. Okay. Recurrence relation. So, we will pick up this one. So, if this is the recurrence relation, and actually if you, this is from n is from 2 to infinity. So, if I put n equal to 1, n equal to 1 is actually 2 into 3 C3 minus, okay. So, that is what you have C 2 C 6 C3, and then you have here. So, alpha into alpha plus 1 and n equal to 1, alpha into alpha plus 2, okay, alpha minus 1 into alpha plus 2 into C1. So, that is exactly you have alpha square plus alpha minus 2, okay. So, this is what if you actually sum it together, this is what you have, okay, into C1, right, alpha square plus alpha minus 2 into C1. So, that is what you have. So, this is exactly, even n equal to 1 you get this expression. So, n equal to 0 you get this expression. So, this actually this recurrence relation is actually valid from n equal to 0 to infinity, okay. So, you can put this together inside by just writing n equal to 0 to infinity, this is what you have. So, let us use this n plus 1 n plus 2 . So, we use this recurrence formula, recurrence relation. So, n plus 1 n plus 2, so let me write into C n plus 2 equal to minus alpha minus n into alpha plus n plus 1 into C n, okay, for every n greater than or equal to 0. So, this I included both the first two terms what we derived earlier. So, okay, this is true. So, this implies what we did is, if you fix n as a natural number, okay, if you fix your n and when n is odd or n is even, what you see is that n is even. So, let us say some 2k, even let us say some 2k. So, if it is 2k you get C2k, okay. So, C0 you are not able to see. So, you get C0, C2, C4, okay, C2 in terms of C0, C4 in terms of C0, like that you go up to C2k in terms of C0, that is what you did, right. So, you put n equal to 0, I get C2 in terms of C0, like that C4 in terms of C2, which you already know this is again C2, C2 is also in terms of C0. So, you have C4 like that, you can go up to 2k is in terms of C0. This is what we did, this is what normally we can get and substitute into the equation, right. If n is even, y1 first solution in terms of C0, you will have all beyond C2k plus 2 will be zeros, okay. So, this one is the polynomial that will stay up to 2k terms, okay. So, you basically you get a polynomial. If n is odd, okay, this is even, if n is odd, say 2k plus 1, in this case what you have is C1, you start with C1. So, you take only odd coefficients C1, C3, C5 up to C2k plus 1. So, in this case here C0, C2, C2k. So, when it is even case, I can write all these things C2k up to C2 in terms of C0. So, you have a C0 coefficient and a polynomial of degree 2k, some polynomial, okay, polynomial of degree 2k. So, here in this case, here also you can get this from the recurrence formula by looking at the. So, if you have n is odd, C1 you will not be able to get it, C3 you can get in terms of C1, C5 in terms of C1 up to C2k plus 1 in terms of, and once you substitute you get C1 times a polynomial of degree 2k plus 1, this is what you get. So, what we do is to derive the formula for Pn, instead of writing C2 in terms of C0 or here C1 in terms of or C3 in terms of C1, we do the reverse way. So, we consider C2k or C2k plus 1, I do not find this one, okay. What we do is I try to keep this as an arbitrary constant, C2k minus 2 I write in terms of C2k. Similarly, so backwards, going backwards, you see that C2 will be in terms of C2k, C0 will be in terms of C2k. So, finally, instead of C0 you will get C2k, again you will get a polynomial. That is also one way of doing it. Okay. We do the same thing. So, you write, instead of calculating, finding the C2k plus 1 from this relation, recurrence relation, you try to do it the reverse way. You keep this 2k plus 1 as it is, and then you C2k minus 1 you write in terms of C2k plus 1, C5 also in terms of this, C3 will be in terms of 2k plus 1, similarly C1 in terms of 2k plus 1. Then instead of once you substitute back, the polynomial solution will be 2k plus 1 into this polynomial degree, same something like similar you will get it. Okay. Now, you fix this constant which depends only on this 2k or 2k plus 1 which is n. Okay. If I can give you this polynomial, that is the polynomial of degree 2k, that means equal to n, this is your Cn. If I give my Cn, which is the coefficient of x power n in this polynomial, okay. So, that I hope I had to give you exactly what is Pn. I will tell you, because you know that Pn is a polynomial of degree n with some coefficient. The same coefficient if you give here, because you know from the Rodriguez formula Pn of x, you know what is the Pn of x, the coefficient of x power n is something which you know from the Rodriguez formula. The same coefficient you also assign here as a Cn, then what you get is the polynomial solution with the same x power n coefficient. Okay. Polynomial solution of the Legendre equation with same coefficient as in the Pn. So, if you know that Pn is a solution and this new polynomial is also a solution with the same coefficient, x power n coefficient, and then if they are the solutions of the Legendre homogeneous equation, which is a Legendre equation, second order homogeneous equation. So, their difference, if you take these two polynomial difference, what happens with the same x power n coefficient, when you take the difference, it will become n minus 1th degree polynomial solution, okay, for the same Legendre equation which is having alpha equal to n. But you know that you do not have n minus 1th degree polynomial solution for the Legendre equation when alpha equal to n, and then it has to be 0, it has to be series, but it is not series here. And because it is a homogeneous equation, there is no other solution except the trivial solution, 0 is the solution. That means the Pn and this new polynomial should be same, okay, either this or this is n, okay, when n is odd, this is this. So, you will see that will give you a formula for Pn, okay, that is the idea. So, let us work out. So, you take this one. So, instead of writing Cn plus 2, so we normally do like this, alpha minus n, alpha plus n plus 1 divided by n plus 1, n plus 2, Cn. This is what we normally do, okay. N is from 0, 1, 2 up to. This is what we do, but instead we reverse this thing. So, if you want reverse this, you want Cn, this you want this to be rather you write reverse way, Cn equal to n plus 1, n plus 2 divided by, sorry, I have a minus, alpha minus n, alpha plus n plus 1 into Cn plus 2, n is from 0, 1, 2 onwards. Okay. N is fixed either even or odd. So, what we see is wherever you start, okay, whenever, so you will not be able to get C0 and C1, right. So, it should start from either 2, 3 onwards, okay. So, that means either this should be, this I can write n equal to n minus 2 if you put it, okay, and this will become minus n equal to n minus 2. So, that, okay. So, if I do this, this side will be Cn, everything in terms of lesser coefficients will be in terms of Cn. So, n equal to n minus 2, so this is going to be n minus 1, n equal to n minus 2 n divided by alpha minus n minus 2, that is plus 2, into alpha plus n minus 1, n minus 2 plus 1. So, this is what you have into Cn, okay, into Cn, n is from 0, 1, 2, 3 onwards. So, once you fix your n, you can write lower coefficients in terms of Cn, fixed n. Okay. So, we use this Cn, this is the Cn is the coefficient of, so if you try to get all these Cn minus 2, Cn minus 4 and so on, let us see what is my Cn minus 4, this is going to be minus n minus 2 here. So, n minus 3, n minus 2, okay, divided by C n minus 2. This is going to be alpha minus n minus 2, okay, alpha minus n plus 4, and this is going to be alpha plus n minus 4, n minus 4 is n minus 3. So, like this you can go on, you can get C n plus, so you already know C n minus 2 from the earlier expression that you can put it. So, you can get C n minus 4 in terms of C n, like that you can get, okay. So, what you once you substitute all this C 0, if n is even, you can get C 0, C 2, C 4 up to C n minus 2 in terms of all these things are in terms of C n. If C n is odd, you can get C 1, C 3, C 5 up to C n minus 2, not C, okay, yeah, C n minus 2. So, if n is odd, you are going up to, so C 1 you are not able to calculate, right, normally. So, C 3, C 5, so n is odd means, so a minimum n is 3, n equal to 3 onwards, right, n equal to 3. So, all these things you are writing in terms of C n in the odd case, okay. So, once you substitute back, what you get is C 0 in terms of C n, some C n will be common in both the cases on the polynomial of degree n, polynomial of degree n. This is what you have. So, this C n I fix as, now I know why my P n is what is my P n of x from the Rodriguez formula is 1 by 2 power n into n factorial n derivatives of x square minus 1 power n, okay. And this one we have already seen that a coefficient of x power n is, what is the coefficient of x power n? The coefficient of x power n, you can actually get it as 2n factorial divided by coefficient of x power n in P n of x is actually equal to 2n factorial divided by 2 power n into n factorial square. This is not difficult to see. If you actually differentiate x power 2n, so you have x power 2n is the polynomial that you are differentiating n times, right. So, if you differentiate n times, this becomes what happens. So, how do you see this? Coefficient as actually coefficient of x power n in P n is equal to 1 by 2 power n into n factorial, which I write here. So, n derivatives of x power 2n is 2n, 2n minus 1 up to 2n minus, if you do twice, if you do it twice, you are getting 2n minus 1. So, you will get up to n minus 1, right, n plus 1 rather, up to n plus 1 you will get, right. If you do 2n, 2 times x power 2n n times, okay, then what you get is x power n coefficient, okay. So, that is the x power n coefficient, the terms will be is simply this, and this is equal to I have 2n, 2n minus 1. So, if you add and multiply n factorial, divide and multiply n factorial. So, what you are getting is 2n factorial divided by 2 power n into n factorial square. So, like that you can get this. So, you use this as your Cn, okay. So, let Cn be 2n factorial divided by 2 power n into n factorial square. If I choose this, what happens to my Cn minus 2, Cn minus 4 and so on, okay. So, you can write first what is your Cn minus 2. Cn minus 2 is minus n into n minus 1 minus n into n minus 1 into n divided by, now alpha is actually n, okay. Now, you fix your alpha is n, n is n minus n plus 4. So, you have 4 times, okay, not 4, so I think 2, okay. You fix it here. So, alpha equal to n, you have 2 into 2n minus 1, 2 into 2n minus 1 into alpha c into Cn. So, what is Cn? Cn is now you fixed it, which is 2n factorial divided by 2 power n into n factorial square. So, this is equal to, so you see that 2n minus 1 goes. So, you have 2n minus 1, you can rewrite minus n into n minus 1, 2n into 2n minus 1 and 2n minus 2 factorial. This I am writing like that. And you have 2 into 2n minus 1 into 2n into n factorial into n factorial. If you write, this is equal to, so n into n minus 1, if you remove denominator, this n factorial becomes, if I cancel this here, what I am left with is n minus 2 factorial. Okay. And you have a 2n minus 1, 2n minus 1 goes, and here n you cancel here 1 n. So, you get n minus 1 factorial. What you have left with is 2n minus 2 factorial, right, 2n minus 2 factorial into 2 power n, and 2 goes here. That is what you have. Okay. That is your Cn minus 2. Now, you get your Cn minus 4. Cn minus 4 is minus n minus 3 n minus 2, okay, minus n minus 3 n minus 2 divided by alpha is, now we fix here alpha as n. So, n minus n plus 4, 4 into 2n minus 3, 4 into 2n minus 3, and what you get is Cn minus 2. So, Cn minus 2 we already know what it is, right. Cn minus 2 is 2n minus 2 factorial divided by 2 power n, n minus 1 factorial, n minus 2 factorial, which is simply calculated now. Okay. You already calculated Cn minus 2, which you put it here. So, this will become, so what you do is n minus 2, n minus 3 you cancel here. Okay. Of course, you have a minus of this, right. So, it is a minus minus plus here. So, in this case what you have is in the denominator, if you cancel here, so it will become n minus 4 factorial. So, this you can rewrite 2 minus 2, 2n minus 3, okay, and then 2n minus 4 factorial you can write. So, 2n minus 3 will go, okay, and here n minus 1. So, this 2n minus 1, this 2 you can take it out here and write n minus 1, this you cancel here, this will become n minus 2 factorial, 2 power n as it is, 2 goes, you have 2, 1 into 2. So, you have 2 factorial either, okay, it will come like that. And what is in the numerator? So, you simply have 2n minus 4 factorial. This is my Cn minus 4. Okay. So, like this, if you go on by induction, you can write Cn minus 2k. How long you can go? If n is even, say let us say 2k, I can go up to n equal to k equal to n by 2. Okay. If n is odd, I can go only up to C1. That means n, if n is odd, you simply calculate n by 2 integral part of it. Okay. If it is n is 5 by 2, so only 2 integral part is, that is 2, okay, like that. So, you take like this, if you write like this is the integral part, bracket of n by 2. So, k will go up to, k is from 0, 1, 2 up to n by 2 as an integral part, okay, integer part, okay, integer part, that is this. So, if by induction you can write 2n minus, so you have a minus. So, if when it is n minus 2 into 2, you have minus, it is plus. So, you have minus 1 power k, 2n minus 2k factorial divided by, this is going to be k factorial, 2 power n, n minus k factorial and n minus 2k factorial. This is what you will get. Okay. Now, simply your solutions, because I have already explained you, if you take Cn which is same as the coefficient of Pn, it has to be the same Legendre polynomial. So, the Pn, okay. So, let us say simply if n is even, okay, n is even, what happens to your y1 of x now? Y1 of x is C0, C1, okay, everything in terms of Ck, okay, and Ck I fixed now, this number, whatever the coefficient of Pn. Then you simply have n is from 0 to n is even. So, n equal to 2k. Okay. So, if you do that, so k is from 0 to n by 2. If n is even, no problem, integral part also is n by 2 minus 1 power k 2n minus 2k factorial divided by k factorial 2 power n minus k factorial n minus 2k factorial. This is what you will get into x power, if k equal to 0, what is this? If k is 0, x power n minus, every time you just, so if n k equal to 0, x power n coefficient, if k equal to 1, x power n minus 2 coefficient. So, every time you have 2k, so x power n minus 2k. So, this is your polynomial. Okay. The way you fixed it, when k equal to 0, when k equal to 0, this is exactly the coefficient y1, coefficient of y1 of x, coefficient of x power n in y1 of x is actually equal to coefficient of Pn x power n in Pn of x from the Rodriguez formula. Okay. Both are solutions, these two are solutions, y1 Pn x are solutions of Legendre equation. y1x minus Pnx is also solution of Legendre equation. What is this one? This left hand side is now, if you have the same coefficient, when you take the difference, this will be n minus 1th degree equation with alpha equal to n. Is it possible? N minus 1th degree polynomial solution you will not get for the Legendre equation with alpha equal to n unless it is 0. Okay. That means it has to be 0, because it is not either you have a series solution or a polynomial solution of degree n. Other solution is trivial solution 0. Okay. Trivial solution is 0. So, you have this has to be 0. Okay. So, that implies y1 of x is nothing but your Pn of x. So, you have a formula, now I can replace with y1 as Pn of x. Okay. This is what if n is even. So, if n is odd also is the same thing. So, n is anything, if n is odd, repeat the same thing, 2k plus 1. You can go, what you can go is, you can go up to 2k plus 1 minus 2, that is the first coefficient. Okay. When you write this, n minus n is 2k plus 1. Okay. When put k equal to 0, n is odd, that is the coefficient, every time 2 minus, so x power n minus 2, n minus 4, you come up to x. Okay. Because it is the coefficient of C1 when it is odd. Finally, so that is why you put this integral part of n by 2. So, you do not make, if n is odd, n by 2. So, that is if it is n is 5, 5 by 2 is simply 2. So, you will have 2 terms, 5, 3, 3 minus 2, so 1. So, you have 2 more terms. So, you go up to C1, C3, C5. C1 coefficient is x, x cube, x power 5. So, that is a polynomial. Okay. So, you have the, in any case, this is what is the case. Okay. For any n natural numbers, you have Pn is this. So, this is the formula you can also use directly to calculate this Legendre polynomials. Okay. And one more property I give you now is just you can easily see that, you have seen that 1 I can write it as P naught of x, x I can write it as P1 of x. Okay. Legendre polynomial, x square. Okay. So, n equal to 1 it is true, n equal to 0 it is true, n equal to 1 it is true. This polynomial 1 x I can write in terms of P0, P1. Okay. What if I write x square? X square, what is x square? So, now what happens to x square? So, let us assume that x power n minus 1 is a linear combination of linear combination of P naught, P1 up to Pn minus 1. So, you see that 1 is linear combination of P0 x power 0, okay. X is linear combination of P1, that is actually x, right. So, is actually linear combination means 0 into 1 plus 1 into P1, right. So, that is again actually this is the linear combination of these two. So, this is if you assume, so this you assume by induction we can assume this. If you assume this, we can now say x power n. What is x power n? How do I calculate this x power n? So, you know that Pn is a polynomial, Pn of x is a polynomial, and this is having x power n coefficient. So, coefficient also you know some, and remaining x you already assumed that up to x power n are linear combination of P0 Pn minus 1, okay. And so, you have x power n is simply linear combination of P naught P1 minus of linear combination of P0 Pn minus 1, okay, plus Pn, this whole thing divided by Cn, 1 by Cn, right. So, what is this one actually? This is simply a linear combination of P0 P1 Pn, okay. So, you can write like this. So, x power n you can say simply Pn by Cn, okay, into Cn by Cn plus you can say minus of 1 by Cn times linear combination of P0 P1 up to Pn minus 1. So, this is nothing but linear combination of P0 P1 Pn because Pn minus 1, okay. So, that is it. So, this implies x power n is a linear combination of this is the proof, okay, implies this is what you get. So, that means any polynomial of degree n is a linear combination of P0 P1 up to Pn of x's, okay. All these are functions of x's, these polynomials, okay. So, this is the property 3. So, I think these are there are many more properties of these polynomials which are really useful. So, when it is useful so most important property is the orthogonal property, so which I have derived in the last video. So, this is enough. You can move on to solve other equations when 0 is a regular singular point, okay. So, these are the we have applied the power series method to the Legendre equation when 0 is an ordinary point, okay. So, now we can look into some second order linear homogeneous equations where 0 is actually a singular point, singular, but it is a regular singular point. So, in the next video we will do this Frobenius method to solve the second order homogeneous equation with 0 being a singular point, but a regular one, okay. So, you know the definition of a regular singular point. So, we will give the method. So, such an equation, so if you have an equations second order homogeneous equation with 0 being the regular singular point. So, either this side or that side, x greater than 0 or x less than 0, you can find solutions. That is the method of Frobenius. So, we will give that in the next video.